Hello everyone, welcome to the EasyPower Tuesday Refresher webinar series. My name is Jim Chastain. While we're waiting for late arrivals to settle in, I wanted to cover a couple housekeeping issues. The presentation is being recorded and we will post the video on the EasyPower website. You'll receive an email notice with the link on how to access that. In addition, we'll make a PDF copy of the slides available on the same link, so you're welcome to access that if you want. I'd be happy to share the examples that I'm going to use, but just as a note, they're all constructed with EasyPower 24.0, which is the latest version, and if you're using an older version, you won't necessarily be able to use them. Open up the examples. You're more than welcome to enter questions in the question box. And as we're in the habit of doing, I'd like to start with a couple poll questions. First poll question is, how often do your projects involve elements greater than 15 kV? As always, there's no obligation or liability. It's just trying to get some feedback on whether or not we're delivering the information that you need. This is actually one of the more interesting webinars that I do because it's not that well understood by the general populace, and once you do understand it, it gives you a lot more insight into the overall topic of arc flash calculations. So hopefully you'll feel the same as we get done. So it looks like we have a quorum. Here's how the folks have weighed in on that. So it looks like the audience is in tune with what we're trying to do today. Great. Second question, what has been your primary tool for calculating arc flash for DC applications? And again, this is another hotly debated topic in the industry. And virtually every conference you'll find presentations on the topic of DC arc flash. And there seems to be a couple different camps, primarily based upon, at least in my opinion, divided by the need to label relatively low volume situations compared to someone that's doing high volume calculations. Let's just leave it there. You'll see when we get there. So it looks like we have a quorum. Here's how people have weighed in. Pretty good split. And I appreciate your feedback. And then finally, the main concern you have regarding medium voltage arc flash involves the potential for single line to ground, line to line arcs, or three-phase arcs. And again, this is a topic that surprisingly is not that well understood by the rank and file, and so it's fun talking about it in more detail. So it looks like we're getting close to a quorum. Let's give this another 10 seconds. And everyone attending today will receive an attendance certificate. Then most people use that to support their extended education credits. All right, let's close this one. Again, a good distribution of responses. And hopefully you'll get some information that's useful as we go forward. Now, just a quick note, what I'm covering and most of the topics that we're touching on today are included in the Practical Solution Guide for Arc Flash Calculations, Chapter 3. So I've included a copy of this PDF booklet in the handout portion of the webinar control panel. So if you haven't already, you may want to give that a look-see and see if you have any questions. Now, just as a reminder, NFPA 70E basically gives us two approaches to arc flash calculations. The first is an arc flash PPE category method. We sometimes refer to it as a table lookup, but in these specific tables, there's AC circuitry, AC configurations, DC configurations, and then in the third table, there's a PPE description that pertains to both AC and DC PPE. So the one caveat that NFPA 70E offers is you can't use both the category method and the instant energy calculation on the same piece of equipment. And that goes for calculating instant energy, and it goes for labeling. So that's another topic altogether. What we're going to focus on is the instant energy calculations, and hopefully we'll all be in alignment by the time we're done. Now, conventional wisdom says if the only tool you have is a hammer, then everything looks like a nail. Well, keeping with that analogy, I think of EasyPower as more like a Swiss Army knife, and the more you understand the functions, the better utilization of the tools you will be able to control. And so all of these, everything we're going to cover today is in the EasyPower feature list that's included in the Arc Flash module itself. Now, looking at IEEE 1584, the 2018 version, they being the IEEE committee are very specific about the range of parameters that are utilized in the model. That includes the voltage range between 208 volts and 15,000 volts. They're very specific. It's either 50 hertz or 60 hertz. It's not anything in between or outside. Voltage fault current RMS, there's two ranges for low voltage, 208 volts to 600, and then for medium voltage, 600 to 15,000. And those are specifically capped for a reason. Likewise, the gaps between conductors has a specific range in the model. The working distance basically is stipulated it needs to be greater than 12 inches. And the justification for that is that anything less than 12 inches, potentially you could be in the plasma, arc plasma ball, and that's a bad thing. So they want to discourage any working distance less than 12 inches. Enclosure dimensions are a fairly important constraint, and basically they establish some specifics using the enclosures that were defined in the original 2002 version. And basically they give us a maximum height or width, a maximum open area, and then a minimum width. And this all has to do with reflections of the energy from the cabinet that the arc is inside or within. Now, with that said, the IEEE 1584 2018 model is described as an empirical model. And that means it was developed to fit the data, and it doesn't necessarily mean there's any linear correlation between one parameter or another over any specific range. In fact, there could be step functions in the way correction factors are applied based upon voltage and current and gap and some of these other parameters. So consequently, the correction factors are valid for a specific range. Now, EasyPower will indicate out of range when we've crossed a boundary as far as the specification itself, but in most cases, it will still give us a value and it's up to us to decide whether or not we want to go with that or not. What I mean by that is illustrated by this particular example, which I call correction factors. So correction factors are typical. The big advantage of the 2018 version of 1584 is they give us not only the range of the variables, but typical values, which is something that wasn't available prior because it's difficult to get the information out of manufacturers. So I'm going to look at a 0, 1 correction factor. Now, as I said, these examples are all developed in EasyPower 20.24.0, and be happy to send you a copy if you wanted to play with, but you can't use it with an older version. Okay, so what I'm talking about, if we open up a data dialog bus for any bus, there's a bus type, and based upon the bus type, this is reflective in the selections in the model of specific characteristics for that generic type of equipment. So the bus type is selected, and then when we go to ArcFlash, there's a number of correction factors down here that are by default annotated or selected. They include working distance, electrode gap, electrode configuration, and enclosure size. And when the default is selected, then these parameters or these numbers are used as correction factors for that particular type of bus enclosure or arrangement. Now, when I go back, well, I'm going to go back to the bus again. If I have a specific setup where I know my electrode gap is different from the standard, then I can use it by selecting user specified and then putting in the actual electrode gap that I measured on my equipment. Now, what I'm going to show or what I'm going to discuss is the fact that whatever I put in there may or may not be in the range that's part of the model. So if I go to short circuit focus, I'm going to select this one bus, fault it, and then look at arrange for ArcFlash. I can see that this is just all default settings. I have the voltage, the fuse is a protective device, the equipment type as we selected in this description is motor control center, and these are default settings for the dimensions of the enclosure, the electrode gap, and then the tool calculates the bolted fault current, and from that it compares the effect on the tripping element, and that gives us the incident energy and the working distance. Now if I compare this against a bus that was described with a 100 millimeter gap, I can see that still the same protective device, still the same designation of type of equipment. Our dimensions are the same except for electrode gap, and this is going to affect my trip time and the arc time, but there's an annotation that this parameter is outside the range that's designated in 1584. So the tool gives me an answer, and it looks like it's about 2x what the default setting was for the previous line item. It's up to me to decide whether I want to accept that or not. And again, it falls under the category of engineering judgment. Likewise, if we want to look at an enclosure size and compare, so I'm just going to fault these three buses. Okay, so when the big so what's being, I guess, uncovered is the fact that there is some nonlinearity as a relationship to some of these parameters, which seems fairly linear, don't necessarily show up. And so that's why we're allowed to use it, and it's up to the engineer to take steps to decide whether that's going to be part of my model or not. Now, working distance is something that's fairly uh, fairly linear because it's applied to the incident energy radiation itself. And it's a well-known fact that the farther away we stand from a radiation source, the lower the incident energy will be by a square of the distance difference between our comparison points. So if we look at a working distance, same fuse, same piece of equipment, electrode type, bus fault current, but now if I set a working distance of 6 inches, my incident energy goes through the roof. And again, that's why we don't want to encourage people to be working within 12 inches of an arc flash hazard. Now, for what it's worth, these plus signs on my spreadsheet give me the ability to see how working distance affects this specific combination of parameters. And so it gives me the results for an 18-inch working distance, a 24-inch, a 36-inch, and these all pertain to the setup for EasyPower short circuit. So if I go back to short circuit focus, short circuit options, arc flash hazard tab, these working distances are what's being represented behind the little plus sign. Fair enough? Now, all right, so that's basically telling you that you're outside of the specific range of the standard model, but it still could be valuable information, and it's up to you to make the decision to accept it or not. Now, just a quick note. And this is a bit of a soapbox for me. The working distance for the label should be something that correlates, in my opinion, to the standard working distance for taking the cover off the bus or off the equipment. And the justification for that is 18 inches is typically the length of the forearm when I'm standing in front of a panel. A lot of people think, well, it would be nice to know what the working distance is for hot work, especially if I have the ability to invoke maintenance mode. And my point is that information, the working distance for specific hot work tasks, may be different than what is required on the label and should be handled on a hot work permit rather than anything that's broadcast or observable by the public. And that goes for maintenance mode. Maintenance mode should be part of a specific task setup. And in my opinion, it's, well, I shouldn't be quite so specific. If I have the knowledge and capability of preventing non-qualified people from accessing the equipment, then potentially having more information at hand for them could be valuable. But then that means I need to have a very sound auditing system and a training system. Okay, so much for soapboxes. Now, all these variations in parameters can be represented in the nonlinearity of the 1584 2018 model is represented by these displays of voltage fault current versus incident energy. And the rust color, the rust color plot is the 14.3 kilovolt range. And then the blue is the low voltage 600 volt range. And they stop, and where they start, the dotted line is where they exceed the prescribed range listed in the model. And 1584 gives us no recommendation on what to do at that point. So that's what all this discussion is about, is what do you do when you're outside the range of 1584? Now, another thing that's excluded from 1584 is the DC systems. So in very plain English, the standard says DC arc flash model is not included. Consequently, they give us some choices. In EasyPower, that choice is a max power method, and it can be applied to any DC systems, including greater than 1 kV, again, at the option of the operator. Now, with that said, there are several papers that are being presented or have been presented at different conferences on this topic, and there seems to be a general consensus that the max power method is relatively conservative, and so there is a move afoot to define, I guess, more or less restrictive standards, but until some agreement is on it in EasyPower, they won't be included. So I want to show how this looks on my calculations. All right, so here I have a system that has both AC and DC components in it. And my DC components are here, and then up here at greater than 1 kilovolt. If I go into short circuit focus, look at my short circuit options, you can see under the advanced tab, I have the ability to apply the max power method to circuits greater than 1 kilovolt. If I don't have that checked, then I come back and fault the system. And look at instant energy. We have instant energy for the AC system and the DC system below 1 kilovolt. And we're excluding the 6,000 volt part of the circuit because of that setting. So again, if I want to include that, I'd apply this checkbox. And then just like in any other case, I'd want to see how the calculations are being made. And here's the voltage, the protective device, the element type, the dimensions, the electrode gap, and then the trip time by virtue of the protective device that's in the circuit. So that's DC. Let me see what we got. Got a question floating in. So Nadim is saying, is it allowed? Are you allowed to operate a breaker that has an instant energy over 40 calories if there's no other way to do it rather than operate it remotely? So what this comes down to, back in the original issue of 1584, there was a recommendation not to work on anything over 40 calories while it was energized. Part of that justification was the lack of PPE equipment for that rating category. In today's market, there are PPE systems that are available in excess of 100 calories. So in the tables that we talk about in IEEE, they do not have an upper limit as long as our PPE rating is equal to or exceeds the calculated instant energy for a particular bus. So the answer to your question is, I'd be real careful, but I would choose any other way before I go that, and made sure I had plenty of room to exit the area. Well, here's a question from Lewis. Will multiple working distance be available in the short circuit view added to the scenario comparison in the future? I'd have to check on that one. There's some constraints on how we do that, but let me get back to you. Thank you for the question. Okay, so that's DC systems. Now, for single phase, again, it's not included in the model, and that's one of the goals of the current committee working on Arc Flash, and that is to come up with a model for single phase. But the current standards suggest that a conservative result could be attained if we determine the single phase fault and then use it in the three-phase model to get the instant energy. And EasyPower can do that with no additional settings. So let's see how this works. So we're looking at single phase. And here we have both a three-phase and a single-phase system. For those of you that haven't done any single-phase modeling, this element here at the top of the feeder indicates that we've picked off B to C for my single-phase supply to this transformer. Likewise over here, this is supplied from A to N. When we go to short circuit focus, fault all the buses. Now I'm applying a three-phase bolted fault as far as the characteristics of the fault. And if you look at it, any fault that I apply is going to translate through the system based upon that particular phase being connected through the connection. So if we look at a range for arc flash, we can see that the voltage, single phase BL1, the bolted fault current is a function of the available short circuit current from the utility. So in this case, we've got the same value, which makes it a little bit, let's change that. So this should make it a little bit more discernible for a single phase fault. Fault all the circuits. So this is showing a three-phase fault, and now a single phase fault removes the three-phase calculations, but it gives me the results for the single phase part of the system. And I can examine those details with the range for arc flash. Now the same kind of warning is that it's outside the range because it's not part of the model, but it's up to me to accept whether or not that this is a valid arc flash instant energy calculation. No, I'm not prepared. So Lewis is asking, can we discuss the variables on the rectifier? That's outside the scope of what I wanted to talk about today. So Hamza is asking, for the DC system, does the model take into account both the inverter and battery contributions? The answer is yes. And we can verify that. If I had a battery Let me go back to that other one. Give me just a second. Now, well, that'll be battery for DC. Okay, so what we're looking for is if we have contributions from motors and DC systems. So if we look at the current, both the buses, we can see battery contribution, in this case of 1,000 amps, into my inverter. I can see loads and motors. There's no point where I've got a battery coming into here, but the answer is yes. It'll deal with contributions from any load or source in a DC system. Okay. So basically that's done without any additional EasyPower settings, just doing a faulted bus and then knowing where to look on my arranged for arc flash. Now it gets more interesting when we have higher voltage or current. And so 1584 makes no recommendation for calculations on systems greater than 15,000 volts. EasyPower gives us the option of using Lee equations for three-phase arcs, or for single line to ground faults, a calculation that's very much akin to ARCPRO. So let's get into details here. So in NFPA 70E, one thing to point out, just as an aside, NFPA 70E is considered a consensus standard. And what that means is it doesn't necessarily hold the letter of the law. If we have a different methodology that's more practical or more efficient in protecting our equipment or our personnel, and it's not listed in the guide, that doesn't mean we're wrong. It just means we need to justify the use of that particular model. So if you have a better way of doing things, then by all means document it, and I think you'll be in pretty good shape. So selecting the Ralph-Lee equations gives us the ability to calculate instant energy and arc flash boundary for a three-phase arc in open air over 600 volts, and it becomes more conservative as the voltage increases. So let's go and see what we're doing here. Let's close this guy. And let's open Ralph-Lee. Now again, this is conservative, and it is a theoretical, it's not an empirical model, it's theoretical, which means so far it's stood the test of time, having been in the market over 25 or 30 years. So I have 145 volt, 1000 volt bus in a couple places, and I have different time elements. Here I have a calculation based on a 5-cycle clearing time. Here we have protection based upon a relay setup. And then here we have a fuse. So let's go into short circuit. Fault all the buses. And what I get is just a calculation on my medium voltage. Actually, no, it's not even medium voltage. It's the motor control center. And it's at 4.16 kV. And that's due to the fact, or I'm not getting any other results, because in my setup of the short circuit arc flash, if I go to advanced, I can select if the voltage exceeds the maximum, which we are talking about 145K, then we would apply the Ralph-Lee method. Likewise, if the current exceeds the IEEE maximum of 106,000 volts, current amps, it would be applied there by selecting those. And giving it a default. Now we've got calculations for all the other buses and the results down here on the spreadsheet. Annotation that they're out of the range, but we know that they're the result of the Ralph-Lee equations. So these are three-phase faults. And they're conservative. So this comes to the question. So any questions on three-phase outside of the 15K volt, or higher than the 15 kilovolt range? The question is there a difference between the pink and blue values? That's a good question, and the answer is yes. Down here, when we have a dark entry, a dark parameter, that means it's using 100% arcing current to make this calculation. When it's magenta colored, that means it's using reduced arcing current as per the standard 1584 recommendation, and this is what tells us that it's been, because it's now part of the model, it tells us that 100% versus some reduced value is being compared. And then these are red because I'm exceeding the setup. These limits, these thresholds here are being exceeded for a specific bus. And if we look at 145K, then anything over 25 calories would be indicated as a threshold buster. Okay, so that's Ralph-Lee and everybody's happy with it. Now we're going to jump into are there less conservative arc flash methods available? I'm not aware of any. There could be some, but most of the concern. So the answer is no. I'm not aware of any. Although there's a lot of papers been generated in IEEE presentations or conferences, there's not been any consensus that equals the suggestion to use Ralph-Lee equations as a backstop. Now, on the other hand, if we look at the applications when most high voltage applies to a bus that's open air, then the concern turns to, well, we're talking about a termination or a phase separation that's considerably more than 350 millimeters, and it could be in terms of feet as far as the separation between the phases. So the concern is more single line to ground faults, and that's where we're going to apply next. So examples of high voltage or medium voltage single line to ground arc flash are used when phase spacing is large enough such that single line to ground is a more likely fault than a three-phase fault. And this is sometimes referred to as the ARCPRO method, but what you'll see, and I'll get into the details, what you'll see is ARCPRO calculates a heat flux. You still need to know what the time element is in doing the calculation. So we're going to set up the bus dialog, calling the elements that we want to be analyzed open air. On the short circuit tab, we're going to go to the Arc Flash Advanced and select open air, and then fault a single line to ground. So let's see how this looks. And this is, again, the standard for this was developed in 2009. I'll get into those details in a second. All right. So again, we have a single line to ground, open air, and in the Arc Flash Hazard tab, we're using all default parameters. Under my setup for short circuit, I want to go into short circuit options, advanced, and apply a single line to ground for greater than 15 kV. And then as I go back and fault the bus, fault all the buses, I want to apply a single line to ground fault. And now I get the results on my one line diagram and my range for Arc Flash. So again, for each of these elements that are elevated voltage, they're outside the range, but they're a single line to ground where the fuse is a protective device, and the trip time is a function of the TCC curve of the fuse itself. And the arc time, consequently, for a single line to ground will be considerably less than if we had a three-phase bolted fault or a three-phase fault in a enclosed system. So what I'm emphasizing here is the importance of including the time element to do the calculation. So where all this came from, any questions on this? This is pretty straightforward as long as you understand you're looking at open air buses and you have a wide spacing where single line to ground is the, I think I'm keeping up with the questions. All right, so a little bit of background on where this came from. And I apologize for the confusion I'm about to throw at you, but it's documented and I'll give you the resources when we get there. Okay. Back in 2009, NFPA 70E produced a table to estimate the instant energy exposure in live line work in overhead open systems from 1K to 800,000 volts. So this was a study that was done by a couple large utility companies, and what they did was calculate the heat flux in calories per square centimeter. And the significance there is the heat flux just tells me what the rate of radiation is coming at me. What I also need to put into place is the time element. And that's where the ARCPRO situation falls apart. I'm not an ARCPRO user, but what I've seen is it provides these heat flux results, and then it's up to me to figure out how that's the time element multiplies this particular number. So these are notes from both the table and the setup. There's two tables. There's from 1 kV to 46 kV, working distance and phase separation. And again, what it's delivering is the heat flux rate. And then the second table goes from 46 to 800,000 volts. And again, it's talking about a transmission rate or a radiation rate per second. And somewhere along the way, I need to understand where the calculation for stopping or eliminating the arc, clearing the arc is going to take place. And that's the advantage of using EasyPower to do this. The point I made, and it's more detail than you want to hear, is I picked 3 different areas and then worked through the directions on what these calculations are, including the air gap as described in the notes. And I get a 1-for-1 correlation between the results we see here and the results that were published in EasyPower. So there's one example, and if you want a copy of this, again, I just have a copy in the EasyPower 24.0, but we put together a 1-line diagram that allows me to apply a single line to ground fault to any one of a number of different buses with both different time elements and different voltage elements. And you'll be surprised how well it matches that chart we just pulled out of the NFPA 70E format. So any questions? I agree. I apologize. I was quite the nerd when I walked through this by hand, but it convinced me that it's much easier just to do EasyPower. So George is saying, is a single phase rating line to line or line to ground? Single phase is line to ground. Now, that's a good question. It's a real good question. In the CFR, let me see what I want to look at. What am I saying? I can produce a single line to ground fault, or I can produce a line to line ground fault. What the setup seems to imply, if I go to my arc flash setup, short circuit options, arc flash setup advanced, it seems to imply that I can calculate 3-phase and line to line. These factors are adjustable, and frankly, we don't recommend any particular value, but they can be used to have results for 3-phase and line to line for open air buses. So this is up to you. I'm just saying we haven't been able to base these on any long-term studies. They're just guess factors. Okay. Finally, so any questions on single line to ground, high voltage, open air calculation method? Let me look at my questions. Are there less conservative arc flash voltage above? Okay, so it looks like we've kind of covered the questions. There's one thing I wanted to cover as well, one more example, and I like it because it encompasses virtually everything I try to proclaim as far as having a procedure to analyze problems in my system. So I'm going to go back to my received a email with a copy of a file from an engineer. He said, Jim, I have a bus here that's not responding. It's protected by a relay, but no matter what I do with the relay settings, it doesn't change the instant energy calculations. And he was talking about this main bus. So when I got it, I went in and said, okay, it's under short circuit. I'm going to fault that bus. And sure enough, it's 233 calories. And this is set for 1400 amps, so something's not kosher. Well, the first thing I would recommend is looking at my range for arc flash. And as I do that, I see it's an open air bus. The tripping device is 9005 1.1, whatever that is. It has nothing to do with the relay. So because I've done this before, I set a named view for that particular device. And it turns out it's a fuse 9005 here. And if I look at current through the fuse, it's 9 amps. So this bus is being faulted. If I look at the details, the device is not tripping because I only have 9 amps coming through the fuse, and so it's never going to clear the arc source, the current source. But for some reason, we've already applied a 2-second maximum, and so that's what the large number is being generated from. So there's a multiplication of errors here. So I'm going to open this up just for grins. And as I do that, I can go back to my main bus and look at my instant energy. And now I see I get a nice civil 7.7 calories per square centimeter. But if I look at my range for arc flash, it tells me it's out of range. It's like, duh, I didn't see this as a 25 kV bus. So let's come back and check our work. First of all, it's already defined as an open air bus. So what does that mean for my calculations? If I go into my short circuit options, see, this is why I balk at somebody that wants to put in 2-second max as a first step in doing an evaluation. My recommendation is this, by concern, is by doing this, you can obscure miscoordination, and that's exactly what's happening in this case. So I'm going to go to my advanced. I'm going to apply open air greater than 15 kV. Now, so the numbers that I'm getting for instant energy is due to the Ralph method application. And I can prove that if I undo the Ralph and apply it, I get 0 results here for instant energy. Okay, so I know where my calculations are coming from. I'm going to go back and do my open air single line to ground model and make it greater than 15 kV. And now let's apply a single line to ground. Now we got a 0.5 calorie incident energy that indeed is protected by the relay. So my point being, if you have problems, if you have a procedure to back up the source of the fault and the timing element of the fault, you can find yourself much more efficiently solving problems rather than just adjusting a relay because it's the closest thing to the bus. I enjoyed that that example. Okay, that's all I had for today. So what we've covered is the different cases of short circuit and arc flash required calculations that are outside the range of 1584. Talked about Lee equations as the upper boundary, although it's conservative. We can do high voltage single line to ground arc flash calculations up to 800,000 volts. And we suggest an application of a single line arc flash result and a DC arc flash result. So hopefully you got something from this. I'll check my questions one more time and hope you have a good day. So Hamza is saying, what is the contact number helpline for contacting when we encounter issues like this? So that's a good question. Let me just show you. When I'm in EasyPower, I always have access to this little support icon here at the top. And as long as my license is current, maintenance is up to date, I have unlimited access to tech support via email or phone. And so what they suggest is click on that button, which gives them the status of your license, and then sending an email to supply@easypower.com, and you're off and running. Now, for what it's worth, you're more than welcome to send questions to me. I may not be as readily available as tech support, but we can help you out if you're having a problem. Okay, have a good day. Thank you for attending.